Hello everyone and welcome back. My name is Mr. Kowalt, and in this video I'm going to show you how to use stoichiometry to solve a problem involving a redox reaction. So let's get into this. So here you're given a 0.376 gram sample of an iron ore, and you're dissolved it in acid, and all the iron in the iron ore is reduced to iron 2 plus. Okay, so then what you do is you take that solution with iron 2 plus and you titrate it with KMNO4. You're given 41, or it takes 41.25 milliliters of this KMNO4 solution, this 0.02140 molar solution, to titrate it. So here's the redox reaction that's occurring. So when you're titrating your Fe2 plus, you are converting it into F3 plus. So you've got this equation here, and now you're going to use it to help you do the stoichiometry. But the first step is to balance this equation, because you've got an unbalanced equation. It's an acidic solution, so you're going to need to know how to balance a redox reaction in acidic solution. So that's the first step. So let's go ahead and do that first. So the first thing you want to do is put down the oxidation states of every atom in the reaction. So the ions already have their oxidation states, because the oxidation state for your ions, for the monatomic ions, is equal to its charge. So iron 3 plus, that's the oxidation state here is 2 plus, and then for manganese it's a 2 plus here. So what about manganese here and oxygen? Well, the rule is that when oxygen is part of a polyatomic ion or a compound, the oxidation state of your oxygen is a -2. So all of those oxygens, each oxygen has a -2 oxidation state. You have 4 oxygens. The other rule now, so the next thing we need to do is find the oxidation state of manganese. The rule is that the oxidation states of the atoms in the molecule or ion should add up to the total charge of the molecule or ion. If it's a polyatomic ion, then it's going to add up to whatever the charge on the polyatomic ion is. In this case, it's a -1. So if this was a neutral molecule, then it should add up to 0. So we know that each oxygen has a -2 oxidation state. You have 4 oxygens. So that's a total of a -8 for the oxygens. And so whatever the oxidation state of your manganese, it has to be such that the oxidation state of the manganese plus the oxidation states of your 4 oxygens add up to -1. So what plus -8 gives you -1? It's going to be a +7. So that means that the one manganese here has a +7 oxidation state. So once we got that done, now the next thing is to separate this into its oxidation and reduction half reactions. Okay, so oxidation is loss of electrons, oil rig. So oil oxidation is loss of electrons. So when you lose electrons, you become more positive. So we got to look for the more positive ones. So here I'll do oxidation on this side. So this will be my oxidation. So we're looking for something that's growing and positive. So iron goes from a 2 plus to a 3 plus. It became more, excuse me, it became more positive. So that means that it lost electrons, so it underwent oxidation. So here we're going to write that half reaction. Fe2 plus goes to Fe3 plus. Okay, now the reduction, I'll write reduction over here. So the reduction half reaction, reduction is gain of electrons. Oil rig reduction is gain of electrons. And so what that means is that the charge is going to become more negative. So we're looking for more negative. So oxygen, we don't really have anything to compare it to. So we're looking at manganese. So more negative or less positive is what we're looking at. So here we're going from a +7 to a +2. So it's becoming less positive. So that's undergoing reduction. So we're going to write our half reaction MnO4 minus, and that's going to go to Mn2 plus. Okay, so now we have the aqueous there. I'm ignoring the aqueous, but we'll come back to that. I'm just saving space. Okay, so now what's the next step? Now we got our half reactions. Now you got to balance the mass and you got to balance charge because this is a redox reaction, charges change, and so we need to balance that as well. So that's special regarding your redox reaction. Normally in a normal reaction, you're just balancing the number of atoms on both sides, but here you got to balance charge. So we're going to balance the atoms on both sides for each one. So we'll do that first. So here we got one atom of iron and one atom of iron. The charges are different, but we're looking at the number of atoms, not the charge. So this is already balanced, so we don't need to do anything there. So here we have one manganese, we have one manganese, so that's balanced. But over here we have 4 oxygen. So, but we don't have any oxygen over here. So the way to do that is we're going to use water. So we're going to use our water molecules in the solution to balance the charge. So since I have 4 oxygens on this side, that means I need 4 waters, 4 water molecules on that side. So now I have, oops, I forgot the 4. I have 4 coefficient. So I have 4 waters, that's 4 oxygens, 1 from each water. And then I have 4 oxygens here, so that's balanced. But now you'll notice I have eight hydrogens on this side, but I don't have any hydrogens on this side. This is where the acidic solution comes in. Acidic means you have H plus ions floating around in solution. So those are going to end up being part of the reaction as well. So we're going to use hydrogen over here to balance the number of hydrogens. So since I have 8 over here, I'm going to need 8 H plus ions over there. So now I have 8 H plus, and now I have 8 hydrogens over there. So now this is balanced regarding the number of atoms. So we balanced the mass, right? So conservation of mass is being held. Now what we need to do is balance the charge. So we're going to now need to use electrons, and we're going to put electrons either as a reactant or a product for each of these half reactions to balance the charge. So here you'll notice this is a +2 charge and this is a +3 charge. Electrons are negative, so we're going to put it on the more positive side. So whatever side is more positive, that's where you're going to add your electrons because those are negative. Since this is more positive, I'm going to add 1 electron to balance the charge. So +1 electron. So now I have a -1 plus a +3 gives me a total of a +2. So that balances with the +2 here. All right, that's done. Easy peasy, lemon squeezy, right? Okay, so now we could do this side here. So here, we got to count the total positive side in here. So since I have 8 positive hydrogens, that's going to be 8 plus a -1 from my polyatomic ion. That's going to be a +7 total on this side. And then on this side, water is neutral, so there's no charge there. And I have a +2 on this side. So this is a +2. So I'm going to add electrons to the more positive side. Since this is more positive, I have to add a certain number of electrons to get number 2. So that's going to be a +5. So I'm going to add 5 negative electrons on this side. So now we can erase that. And so now I have 5 negative plus 8 positive. That's going to be negative. That's going to be +3. And then plus the negative here, that's going to be a positive 2. That's going to balance with the positive 2 on this side. So now both half reactions are balanced in mass and they're balanced in charge. We balanced the number of atoms on both sides, and we balanced the amount of charge on both sides. Now we need to add the two half reactions together, but before we do that, we need to make sure that the number of electrons for each of these is the same, because when we add the half reactions together, we want the electrons to cancel out. Why? This is a redox reaction. Remember, oil rig. Oil oxidation is loss of electrons. Reduction is gain of electrons. If something is losing electrons, the other thing is gaining, and the number of electrons has to be the same. So if one side is losing electrons, then the other side has to be gaining those 5 electrons too. So you'll notice there's 5 electrons here. There's only 1 electron there. So we're going to have 5 electrons there. And the way you're going to do that is by multiplying the whole equation by 5. So that means I'm going to have 5 Fe2 plus going to 5 Fe3 plus 5 electrons. Now I have same number of electrons for both my oxidation reduction half reactions. Now I'm just going to add them together and I'm done. Well, not quite. We need to make sure everything cancels out appropriately. So here, the 5 electrons and the 5 electrons are going to cancel out, so we don't need to worry about those. So when we add this, we're going to add the reactants for both half reactions together. So we're going to have 5 iron 2 plus ions for this half reaction, and then we're going to add these two. So plus 8H plus ions plus MnO4 minus. So that's the reactants put together. Now we're going to put the products together. So we have the product here, 5 Fe3 plus as a product for this half reaction, the oxidation half reaction. Now we're going to add the products from the reduction. So that's going to be plus Mn2 plus 4H2O. And there we have our equation. Now we need to make sure that we don't have the same thing on both sides. If we have the same thing on both sides, then we're going to have to cancel out to make sure that we only get it on the other side. So here we have 5 Fe2 plus. There's no Fe2 plus here. 8 hydrogen H plus. We don't have H plus here, so we don't have to worry about that. MnO4 minus, not on here. So this is good. This is our balanced redox reaction. So that's a good review for how to balance a redox reaction in acidic solution. So now we're going to use our balanced equation to use stoichiometry to solve this. So I'll be right back. I need to erase this and we'll start where we left off. Okay, so now that we're back, here I have the balanced redox reaction here. So now that I have this balanced redox reaction, I can now use the information they're giving me, use the stoichiometry to solve the problem. So, but if you still struggle with how to balance redox reactions, you can see my videos on balancing redox reactions in both acidic and basic solution. I will link the videos in the description below. All right, so they're giving us this sample of iron. So it's 0.376 grams of iron ore, and it has a certain amount of iron in it. They used acid to get the iron in a 2 plus state. And then to figure out how much iron was in that acidic solution, they used titration where they added a certain molarity of KMNO4. So in a titration, you have this in the burette. This would be your solution in the burette. You know the concentration, and this is the amount from the burette that you had to add to titrate all of your, or neutralize all of your F2 F2 plus. Basically, you converted all your F2 plus to F3 plus. So, so where do we begin? So we know if we could figure out the number of moles of the MnO4, if we could figure out how many moles of MnO4 was added to neutralize or react with the Fe2 plus, then we could use the 1:5 ratio as a mole ratio conversion factor to convert from the moles of MnO4 minus to moles of Fe2 plus. And then once we have moles of Fe2 plus, then we could figure out what they want to know. Okay, so because right now the question is to remind ourselves is to determine the mass percent of iron in the iron ore. So if we could figure out the number of moles of Fe2 plus that was titrated, that would end up being the number of moles of iron that was in the iron ore. We could convert that to grams using molar mass. And then once we know the grams, we can then take the grams of the iron that we found, divide it by the total mass of the sample, multiply by 100 to get our mass percent. Okay, so let's do that. So how do we get the moles of MnO4? Well, they gave us molarity and they gave us volume in milliliters. So we could use your molarity as a conversion factor because molarity is a relation between moles and liters. So if we can convert this to liters, we can then use this as a conversion factor to convert to moles of your KMnO4, which is the same number of moles as your MnO4. The potassium here doesn't matter. So you might be wondering, well, what happened to the potassium? It's a spectator ion. It's not involved in the reaction. So in the reaction equation, notice that they left potassium out because it really is not involved in the reaction at all. And so it doesn't matter. All right, so we have 41. So we'll start with 41.25 milliliters. Put that over 1. And then we have to convert milliliters to liters. So remember, to figure out what the relation between milliliters and liters is, what I do is I take the two units and I put them together. So milliliters is equal to liters. So a certain number of milliliters is equal to a certain number of liters. I always put a 1 with the prefix unit. So since this has a prefix milli, I'm going to put the 1 there. And then whatever the prefix multiplier is, I'm going to put that on with the base unit. So milli is 10 to the negative 3. So that's going to be 10 to the negative 3. And so now I have an equality. I'm going to use that as a conversion factor. So since I have milliliters on the top, I'm going to put 1 milliliter on the bottom. And then I'm going to put 10 to the negative 3 liters on top. So 10 to 3 liters. So milliliters cancels out. Now I have liters. Now I can use the molarity as a conversion factor. I know that this means that you have 0.02140 moles per 1 liter. So I'm going to put 1 liter on the bottom. So this is going to be liters of your KMnO4 solution. So KMnO4 solution. And this is your milliliters of your KMnO4 solution. And then we have the number of moles on top. So 0.02140 moles of, and that's going to be moles of your KMnO4. Okay, so now you have moles of KMnO4. That's the same as the number of moles of MnO4, so you don't need the K in there. So since a 1-to-1 ratio, your KMnO4, the moles of your KMnO4 is equal to the moles of your MnO4. So same number of moles of your MnO4 minus. And now that we have moles of MnO4 minus, we can now use our balanced equation to convert from moles of MnO4 minus to moles of iron 2 plus using the mole ratio 1 to 5. So now we're going to set that up. I'm going a little crooked here. So I have moles of KMNO4 on the top. I'm going to put moles of KMNO4 on the bottom. So 1 mole of KMNO4 minus on the bottom. And now I'm going to have 5 moles of Fe2 plus. So 5 moles of Fe2 plus on top. So moles of KMNO4 cancel out. Now I have moles of Fe2 plus on top. Excellent. So now I have the moles. So now I need to convert moles of Fe2 plus to grams. So that'll be, once I get grams, then I can divide that by the total sample. So let's go ahead and do that. So I need the molar mass of iron. The fact that this is a ion, that it has a 2 plus charge, doesn't affect the molar mass. So if we look at the molar mass, let's look up the molar mass really quick. And so the molar mass of iron is 5585. So that means that 1 mole of Fe2 plus goes on the bottom to cancel out moles, and that's going to be 55.85 grams of Fe2 plus on top. Let me double check that again just to make sure. 5585. Yep, 5585. Okay, so moles of iron cancel out. Now I have grams. So now all I need to do is calculate the amount of grams. So let's go ahead and do that really quick. And here we go. So I'm going to calculate, that's 41.25 times 10 to the negative 3 times 0.02140 times 5 times 55.85 divided by 1, 1, 1, 1, 1, all ones on the bottom. And so that gives us how many grams? It's going to be 0.2465, 0.2465. Let me add another digit, 0. Okay, grams of Fe iron. So now that we know the grams of iron that was in original sample, they want the mass percent. And so remember, whenever you do a percentage, it's going to be part divided by the whole, multiplied by 100 gives you the percent. So here's our part. This is part of the ore, part of the iron ore is iron, which is this amount, and this is the total for the iron ore sample. So this is our whole, this is our part. So we're going to take the part, 0.24650 grams divided by the whole here, 0.376 grams. So this is Fe, this is the iron ore. Okay, so what about the sig figs here? So we need to make sure we know what sig figs are here. So remember, the rule for sig figs when you're multiplying and dividing is that your answer should have the same number of sig figs as the least number of sig figs that you multiplied and divided. So here we have 4. This is exact, so we can ignore that. Here we have 4, because this 0 is significant. Trailing zeros are significant if they're at the end and you have a decimal point. Zeros in the front of the number are never significant, so this is 4. this is exact, and this is 4. So the least number is 4. So 1, 2, 3, 4. So that 0 is not significant. So we'll underline the 5 here. So when we do our calculation, oops, I forgot to multiply by 100. So we got to multiply by 100. And so let's do our calculation. So this divided by 0.376 times 100 equals, and we get 65.560%, but we're allowed. So here we have 4 sig figs. Here we have 3 sig figs. So again, we're dividing. So that means our answer can only have 3 sig figs. So we got 1, 2, 3. So it ends there. This is a 6. So that means we round this up to a 6. So our final answer is 65.6%. So that is the percent mass of iron in our iron ore. I hope this was helpful. I hope you enjoyed it. I hope this was a learning experience. I really want to make sure you are learning. If you like this video, please hit the like button there. Hit the subscription bell. Subscribe to my channel. Hit the notification bell so you can be notified for other videos I put out. And please put a comment in the comment section. Let me know what you think. And if you have any questions I can answer. Thank you very much for joining me. Have a great day.